I promised this a while back, so I'm finally getting to it. I'm going to go ahead and draw our electric motor. We've done a lot of work with that, and we ought to get some more. We ought to get some more life out of it, I guess, is what we ought to get here. Um, we're going to have our electric motor here. Uh, what I'm going to do on this time, so even though, we've got our equations and things like that, all of this stuff can kind of be uh, considered to be a black box. And what I'm going to do is I'm going to hook this electric motor, the gear output, I'm going to call that the pinion, and I'm going to hook it to a rack so that we get rotational to linear conversion here. And what I could do, I'm going to put this onto a spring that's pushing a mass. And sometimes I'll go ahead and hook a damper between these two things. That adds just a slight amount of complication that I want to try to avoid at this point in time. So actually what I'm going to do is I'm going to hook the damper to the outside wall. Another way of looking at that is that, maybe this is sliding on a viscous surface. So we're going to have a damper that looks something like that. Now, before we start, I think I'd like to just talk about the mass spring damper system. And what we can see is that for the mass spring damper system, there's an X, and then there's going to be X of M. And we've already done a free body diagram for this when we did our spring system. What we've done here is we're going to look at mx double dot. We're going to look at bx dot. And then on this side, what we're going to see is we're going to see that we've got a k. And this force, if I move, let me put this force in the other direction. Because if I move if I move this in a positive direction, this force gets bigger. So this is x. I'm going to call this one xi because that's the x input. And then if x itself, x sub m, and I should have put my subscripts on each one of these also, minus xm, right? So if we look at what the equation of motion is here, mx double dot plus bx dot minus k xi minus xm equals 0. And what that's going to do for us is that's going to give us this set of equations, which is going to be mx double dot m plus bx dot m plus k xm is equal to k xi. We've done a lot of work with this already. Well, one of the things that we can do is we can look at what the g sub m, the mass transfer function, is. So that part of it, we'll call that g sub m. And what we're going to take the Laplace transform and find out what the transfer function is. It's just going to be k. This is ms squared plus bs plus k. I should have written this. This is x over xi. And I'll let you verify that. Now, we also did a lot of work with our electric motor once upon a time. And what we know about an electric motor is we have equations for an electric motor that look something like this. So there's going to be a little bit of plus and minus sign work that's going to go on here, but I'm going to draw the free body diagram for the motor. We did this in class. You can go review some of those notes. So I'm just going to go ahead and let the gearbox be built in here. So that's the gearbox. Here we've got the plus and minus. This is the input voltage, Vin. And what I'm going to do here on the output is I'm going to look at this this radius r, I'm going to call this the plus theta out direction. And if you remember, in our motor analysis, we talked about a disturbance force. A disturbance. So there's two ways. You can move this motor either by you can move this motor in a positive direction either by putting an input voltage on it that makes it move, or you can move it in a positive direction by putting a disturbance on it that moves. Now, in this case, we don't have a disturbance. So I'm going to cross out the disturbance. But if we had the disturbance, once upon a time, we had this block diagram. So we don't have a disturbance, but what we do have is we have a force that's acting on, I'm going to put the force this direction. I'm going to say F sub m. So that's a force from the mass. When I draw the free body diagram, for this is going to be a little confusing, but I'm just going to draw it this way. So I'm just going to completely ignore this whole force here. We can figure out what it is later, but for right now, I'm just going to ignore it. And what I'm going to do, I'm going to say, if I'm going to move this xi in a positive direction, I'm going to push on the motor with a positive F sub m. So even though we're doing a free body diagram, what I'm going to do is I'm going to say that these two forces are so small, so I don't care. We'll revisit that in another time. But what that means is that I can go back from my notes and I can say, oh, I know how motors work. Vn is Km. It's the gear ratio over the resistance on the motor. Now I'll leave this disturbance in here. We'll come back and plus, minus. This is a disturbance plus. We're going to come back and look at that, but this is going to be 1 over J equivalent S plus B equivalent. Then this is going to be theta out dot. And this is going to be theta out. Nothing there, theta out. So we have that block diagram. We've used it before. And what we know is that J equivalent is equal to the motor inertia times the gear ratio squared. We'll get that from the manufacturer. If there's any output inertia, in this case we're not going to have any output inertia, we'll just leave that to be 0. We know that B equivalent is equal to anything, it's the motor Bm n squared, it's the motor damping squared, plus if there's any output, if there's any damping right here, and again, I'm just going to neglect that for now. But we know that even if we neglect everything on here, in fact, I'm just going to neglect this one too, plus we know that there's still the back EMF, which is the back EMF constant, the motor torque constant, n squared over resistance on the motor. So we know that there's a little bit of damping on that thing. Now, in one of the homework problems, we went through and figured out exactly what all those numbers are. And what I'm going to do for this one is I'm just going to make up some numbers because I want to illustrate a different point. And I'm just going to say that here's what the motor is going to look like. The motor is going to look like Vn 1 over S plus 4 times S, where this is theta out. Now, once upon a time, for a real motor that we used, it was a 541 over S plus 58 times S. If you go back and look at your notes, you'll see that one. So what I'm going to do here is I'm just going to define this one. See, I used G of the mass, and now here's G of the motor. I'm going to call this G electric motor of S is equal to the output, theta out, over the input, which is going to be theta out over the input, which is V in, and that's going to equal 1 over S squared plus 4S. Okay? Okay, well, now that we've got a lot of done an excessive amount of analysis, now we can just be control systems people. I'm going to write the transfer function for the motor. This is a G electric motor. And what that's going to give me is theta out. There's a little bit of geometry that I probably needed to deal with here a little bit, and that says that when I have theta out, and I look at what this is going to be X equals R theta out, right? So we have a little bit of geometry here that we can figure out. X is equal to R theta. So let's go ahead and put that in here. X is equal to R times theta. That gives me X sub I, right? That's the same as X sub I. And then what we can just write down here is we're just going to write G sub M of S, both of those should be S, and that gives us X of M. That's easy. Block diagrams. Let's expand these block diagrams ever so slightly, just so that we have a little bit here. We're going to put here's V in. This is going to be a 1 over S times S plus 4. This is going to be R. And this is going to be, so this is theta out. This is Xi. This is going to be, sorry, I'm going to do one last thing here. Look, I'm going to change this one. I'm going to do, this is going to be K over M divided by S squared plus B over MS plus K over M, which I hope all of you would be able to remember here is going to be omega n squared over S squared plus 2 zeta omega ns plus omega n squared. I'm just going to make up some numbers for this one too. I'm going to say that omega n squared is equal to 32. And I'm going to make 2 zeta omega n is equal to 8. Now, for this particular one, what you're going to find is that that gives me an omega n is 5.6 and zeta is equal to 0.71. And so if we wanted to look at what the response of that system would be, it's going to have, so if we do that, the frequency is equal to 2 pi over omega n, that's about 1 second. So it's going to have a period. Our spring is going to have a period of about 1 second. And it also has a damping ratio of 0.707. So really, by the time that if I just put a unit step input of that one, you know, it's going to damp pretty quickly. And we can describe that using our generic, kind of our generic response characteristic curves. But here's a system that we have. This is a perfectly good system. And, you know, it might be that what I'd like to be able to do is control the output of that, you know, sure. Let's go ahead and do that. Let's control the output of this system. So did I say the word control? That means we're putting a KP. We're looking at XM desired. And we're going to compare that with XM. I should put this as XM. And there we've got a control system. So we can go ahead with our block diagram algebra and do all the work that we need to do, but why not? Why don't we just use the root locus technique to design this system? We can, of course, find out what the transfer function for this system is. T of S, the closed loop transfer function, is the output over the input, which is the output is going to be XM over XM desired. And what we can do is we can just say it's the numerator of G. Oh, here, I'll write that formula. It's the numerator of G times the denominator of H divided by the denominator of G times the denominator of H plus the numerator of G times the numerator of H. And that's going to be numerator of G, KP, R, omega n squared, numerator of G times the denominator of H, which is just 1, divided by the denominator of G, S squared plus 4S, denominator of G times the denominator of H, S squared plus 2 zeta omega n S plus omega n squared, plus the numerator of G, KP, R, omega n squared, times the numerator of G times the numerator of H, which is just 1 again. So here's what our transfer function looks like. Like I can multiply that all out. Oh, no, sorry. I have my parentheses in the wrong place. Thank you. You know, one of the things that I'm going to look at right away, I'm going to look at the steady state gain. In this particular case, steady state gain, S equals 0. S equals 0 gives me 1. So this will be a good control system. I just have to figure out what gain, what K to use. All right, so let's just go ahead here and we'll figure out. I'm gonna just repeat this up here again. This is going to be, so the open loop system looks like this: 1 over S plus 4, 1 over S, and this is omega n squared over S squared plus 2 zeta omega n S plus omega n squared. There's an R here. Don't want to forget that. Let's make R equals 1. That's just going to be, so we're going to want to put numbers into all this thing. So we know what the root locus rules are. I'm just going to cheat just a little bit and look ahead and try and remember what I'm, okay, so how big do I need to make this whole thing to make this work out? Okay, well, we might have to draw this a couple of different times, but let's just go ahead and try and get this to work out. If I just try to do this by hand. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So I'm going to try and do that. 1, 2, 3, 4, 5, 6, I don't know. 1, 2, 3, 4, 5, 6. Good luck. Maybe I've got that right. Maybe I don't have it right. So, step one, we know that the root locus starts at the open loop poles. So, okay, so it starts at the open. These two open loop poles are easy. S equals 0 and S equals 4 minus 4. So we know what those roots are. I'm going to Okay, so I could do this with protractors and all that stuff, but we figured out earlier that for these roots, we knew that omega n is 5.6 and zeta is 0.71, close enough to a 45-degree angle, I think. Can I just estimate it at a 45-degree angle here? And then I'm going to, I don't know how to, I always do this in a little bit different way, but let's just see. This is about 5.6, so here's about 5.6. So this is the distance of those poles. One, two, three, four, five. Boy, I must not have. Let's just see. This isn't to scale, I don't think. 1, 2, 3, 4, 5. Oh my goodness! You see how bad I am up there. Oh well. We'll just estimate it anyway. This is just a rough sketch, so that's fine. That's what we're trying to do. So this is going to be. So what we know is that in this, the poles at this side, these are omega d. Omega d is equal to omega n times the square root of 1 minus zeta squared, which is 7 times 7 is 49.5. So that's I should do that math. Anyway, okay, that's fine. You do that math. We're just gonna calculate all of these pieces here. So step one, we need to know, so real axis start at poles. 2, real axis segments. Real axis segments. So we know that the real axis is to the left of odd number of poles and zeros. Three, end at zeros. Oh, there's no zeros on this one. So these zeros are infinite zeros. So we know that we have 4 zeros, and we're going to look at theta of the asymptotes is going to be 2q plus 1 times 180 degrees over number of poles minus the number of zeros, number of finite poles, and this is for q is equal to 0, 1, 2, and 3, where 3 happens to be the number of poles minus the number of zeros minus 1. And if you go through that, this is basically, this is just 45 degrees, so the asymptotes are at 45 degrees plus or minus 45 degrees, so they just form an X somewhere. But what we do have to do is see where the asymptotes lie on the S-plane. Where do they lie? It's 5 is the asymptote intercept point is equal to the sum of the poles minus the sum of the zeros over the number of poles minus the number of zeros. One of the things you can think about is that poles, this is like a scale, and the imaginary axis, it's like these things push up. X's push up, and if you have any zeros, they push down, and it's like the center of effort for all of these things. But if we're going to do this sum of the poles and the sum of the sum of the poles, sum minus the sum of the zeros, this is going to be 4. Oh, that's what I was trying to do all this stuff. This is 4 plus 4j. I did do that math somewhere. I just couldn't remember it. And this is 4 minus 4j. So that's minus 4j. And this is, So I was pretty accurate here. This is a minus 4 minus 4j. This is minus 4 plus 4j. All right, so if we look at the sum of the poles and sum of the zeros, it's going to be 0 plus 4 plus 4 minus 4 plus 4j plus 4 minus 4j all over 4. Number of poles minus the number of zeros, which is 4. That's going to be 12 over 3. That's going to be 3. So the intercept point is at 1, 2, 3. This is sigma asymptotes. Sigma asymptotes is right here. And so we can just draw plus or minus 45-degree lines. I'm just trying to see what should I do for colors here. Let's just draw black. Let's draw our y-intercept lines this way. I'm just going to still do about 45. If I had a shred of self-respect, I would get out my protractor and I would draw these things. But oh well, I'm just going to draw the asymptote lines. Now we might like also want to know exactly where are we going to put where does these two poles move towards each other and they break away. And we might be interested in knowing where they break away. And there's a couple of different ways of doing it. We can do we can look at so I'm gonna just, this is kind of an aside, and I'm going to break away here, and I'm going to just do this a couple of different ways really quick. We can talk about that there's a polynomial in S that we're going to, let's start here. 1 plus KGH is equal to 1 plus K1 over S plus 4, S squared plus 8s plus 32. So that's a polynomial in S that we can do is equal to 0. So we're going to set that polynomial P of S, and we're going to set it equal to 0. And let's see, so this is going to be K is equal to minus 1 times S plus 4, S squared plus 8S plus 32. We have to take the derivative of this, right? So we have to say dk ds is equal to 0 minus 4s cubed plus 36s squared plus 128s plus 128. And it's hard to find. There is a closed form solution for a cubic, but it's hard to find. You can just use MATLAB to do it. It's 1.57, or there's more than one root, but we'll just do 1.57. Another way to do this is just to look at what here's P of S is, and here's S, and we'll just put some trial values in it. When S is equal to 0, P of S is also equal to 0. When S is equal to minus 1, P of S is equal to 75. When s is equal to minus 1.5, p of s is equal to 85. When s is equal to minus 2, p of s is equal to 80. When p of s is equal to when s is equal to minus 3, p of s is equal to 51. When p of s is equal to 4, minus 4, p of s is equal to 0 again. And then we could just draw this, like, right? So here's a minus 1, minus 2, minus 3, minus 4. And we could just draw these numbers. We put these numbers in, and we find out where does the peak go. And sure enough, if you went and looked at this peak, it would be 1.57. All right. So even though we know there's a formula for that kind of thing, you know, for in a lot of cases, you can just in a lot of cases you can just kind of estimate where this is. I said it's 1.57, so you know that makes sense. Is where the breakaway points are going to be. Here's the breakaway points. Now, there's one more kind of an important piece of what we can look at here. One of these sets of roots is going to come out. Let me use a brighter color for this. One of these sets of roots eventually is going to come out here. So we know that when k gets big enough, we know that the roots are going to come out onto these asymptotes, but we don't exactly know what's going to happen in between. I'm going to look at the root locus very close to these points, and in order to do that, I'm going to slip aside here. I'm just going to make a quick sketch of on another page just to keep kind of the mess down. And so what I'm going to look at here is I'm going to look at this point. So here we've got s equals 0. Here we've got s equals minus 4, s equals 0, s equals minus 4, and here we have minus 4 plus 4j. So we've got that s. And we've got down here, we'll have this other one that's also going to be minus 4 minus 4j. Sorry, maybe I should have put that better. But here's what I'm going to do. I'm going to say, I don't know, I don't know how this, I'm going to do it over here. I don't know how the root comes off. Like it might come off this way and head up to those roots. It might come off this way and head up to those roots. I don't really know exactly how it works. And so what I'm going to do is I'm going to take a test point very close. So in my mind, this is going to be very close to this root. And I'm going to look at the angle criteria. So I've got k, so 1 plus kgh equals 0. I've got kgh equals minus 1. And from that, I have two things. I have the magnitude criteria, which says k is equal to the magnitude of k is equal to the magnitude of 1 over gh. We're going to use that in a minute. And we're going to say that the angle of kgh equals minus 180. The angle of kgh is equal to minus 180 degrees. Plus or minus K360, right? So you can just go round and around and around as much as you want. And so what I'll do here is I'm going to look at what is the angle. So this is the vector. Oh, darn it. All right, now I have to use a different color because I messed up. Ignore that line. So this is the vector. If this is s, this is the vector s plus 0. If this is the vector, this is the vector s plus 4. This is the vector s plus 4 minus 4j. And this is the vector S plus 4j. So now we've got all of our vectors there, right? And so what we can look at is that the angle of KGH, so the angle of K doesn't matter. It's the angle of, let me write down what KGH is. K doesn't matter, but we know that we've got a vector here, S plus 0, S plus 4, times S plus 4 minus 4j, the angle of S plus 4j. So I'm going to write that in terms of the angle of KGH is equal to, it's going to be minus theta 1 minus theta 2 minus theta 3 minus theta 4. So, because this is the angle, theta 1 is equal to the angle of S plus 0. But because S plus 0 is on the denominator, it's got a minus sign in front of it. Here's going to be the angle of, this is theta 2. Here is theta 3. And now, this is the one I'm really wanting to get to here. This is theta 4. I don't know what that angle is, theta 4. All the rest of them, I more or less know what all the rest of them are. This angle here is about theta 1, minus 135. That's about 135 degrees. So theta 2 is about 90 degrees, right? It's almost right below it. Theta 3 is also 90 degrees. But I don't know what theta 4 is, but I know this has to be minus 180 plus or minus K360. Once I plug in here, it tells me that theta 3, this gives me that theta 3 is going to be minus 135 degrees or plus 225 degrees. So minus 135 degrees, so this is minus 90. So minus 135 degrees, I kind of, by accident, just drew this in the right spot. This is theta 4 is equal to 225, or theta 4 equals minus 135. Either way you can look at it. All right, so now we've got a pretty accurate rendition of our root locus. We kind of know that this guy is shooting off at about a 45-degree angle. Well, 135. So these two shoot off with about a 45-degree angle. And this one comes off here. So, you know, we can kind of just now sketch this in. And again, I'm going to invite you to use MATLAB's rLocus command to check my work. So here's the root locus. We've got a perfectly good root locus now. And we would like to say to ourselves, I wonder where I should put the roots of the characteristic equation for this system. I wonder what I should do. Why don't I choose a damping ratio that I'm comfortable with? I'm going to choose desired root locations that are going to be on the plus or minus 45-degree line. So I'm going to choose those as desired root locations. And now I'm going to use the magnitude criterion. I'm going to use the magnitude criterion to, this says that K1 plus KGH equals 0. That means KGH equals minus 1. That means K, the magnitude of KGH, is equal to 1. That means K is equal to 1 over the magnitude of GH. And what we can do is just break this GH into its components. K is equal to, so this is the magnitude of S plus 0, magnitude of S plus 4, magnitude of S plus 4 minus 4j, magnitude of S plus 4 plus 4j. Now I don't want to forget these other things here because I have an omega n squared here and I have an r here. So I don't want to forget those two things either. And if I want to find out what the magnitude of those pieces are, I'm going to draw those in. So if I want a k that will meet this criteria, I just have to measure the length of each of these roots. This is s plus 0. This is s plus 4. Here is s plus 4 plus 4j. And this is s plus 4 minus 4j. And so all I have to do is measure those things. I don't have a good ruler, so I'm going to do the poor man's measurement system here. Let's just make, this is 0. So that's the distance s plus 4. Let's call that 1.5. Is that okay? 1.5. What's the distance of this? Length of this one is to here. Let's call that 1, 2, 3. 3. What's the distance from here to here? One, 2, 3, 4.25. 4.25. What's the distance from here to here? Graph paper clearly would help here, right? 1, 2, 3, 4, 5, 6. 6. And so what did we say? We said that r was equal to 1 and omega n squared is 32. Omega n squared is 32. And so what we can do is we can say k then is equal to 1.5 times 3 times 4.25 times 6. That should give us our value of k. I think I calculated this. I don't know. So I wrote down the number 130, but that doesn't seem right. We can multiply this out. 6 times 4 is 24, times 3 is 75. 1.5 times 75 is 110 divided by 30. I'm going to call that 3. Well, I'll let you do the numbers. And then, finally, we can go back to our original transfer function that we've gotten. We've already written out the transfer function for this. We've got the transfer function with the k in it. We can do a root locus. We can look at the transfer function and see that it matches what we expect it to match. We can use the r locus command. And then we could even do a Simulink diagram. We'll do that later also.